Cool. Well, thanks so much for coming. OK, we'll see how this goes. So I'll talk about some work based on, I guess, 2 different papers, one with my student, Mingde Chao, and that appeared in last summer's Colt. And that's kind of the motivation slash jumping off point for what I really wanted to talk about, which is sort of described in this paper with Justin Chen, who's an undergrad who's applying for PhD programs. He's fantastic. You should admit him. We should admit him. And with Paul Valiant. OK, so the sort of backdrop to this is the sort of following. So the traditional view of learning or estimation, you typically have some strong distributional assumptions on your data. Like you assume that maybe your test set is drawn independently from some distribution. Your training set is drawn independently from maybe the same distribution. Or maybe data is drawn according to some exchangeable something or other. And that's kind of the traditional view. And then there's sort of things like the robust learning framework. But even there in the robust learning framework, there's still this strong distributional assumption. It's just maybe you assume that most of your data is drawn from this nice distribution. And then some adversary maybe perturbs some small fraction of your data. Or maybe some adversary contributes a small fraction of data. So that's like sort of contamination model. And the stuff I wanted to talk about is sort of based on this question of, can we get rid of the distribution on the data completely? So what if data is worst case? What if we don't, we want to make no assumptions on sort of the data itself? What can we hope to do? So obviously, at some point, we'll need some assumptions on something. But what if we sort of want to avoid assumptions on the data itself? Can we still do anything? And so one response is, well, yes, there's been decades of work on online learning, which sort of, in many cases, assumes a worst case data feed. So that's one positive answer. Are there other sorts of positive answers to this question? What can we do with sort of worst case data? So in the first part of the talk, I'll sort of mention some things about selective prediction, which sort of in a nutshell, one of the punchlines is, well, you can accurately predict the future if you're sort of allowed to choose when you make your prediction in some sense. And the second part will be a much more general framework for dealing with worst case data, leveraging some assumptions on how your test and train data is partitioned. So the data points themselves are worst case, but there's some randomness in which points end up in your test set, which in your train. And we'll see where that comes. OK. So for the first part, consider the following game. So it's a game between Alice, and we can think of her as sort of the universe, and Bob. And the game's as follows. So the universe, or Alice, has a secret length n vector. You can think of it as being a binary vector, or maybe they're real numbers bounded between 0 and 1. It doesn't matter. And each day, you're allowed to ask. You can either ask for the next bit. So day 0, you say, or day 1, you say, what bit is it? And Alice will say, oh, it's 0. The next day, you say, oh, tell me another bit, 1, and so on. Or at a given time, you can say, I've heard enough. I'm going to make a prediction about the future. And the form of the prediction is you're going to try to estimate the mean of the next couple of bits. So after seeing the first 2 bits, you could say, I predict that the average of x3 through x7 is 3/5. OK, and at that point, the game ends. Alice reveals her sequence. And you see the actual mean of those next few bits. And the game ends, and we incur a loss, say the squared error between our guess and the ground truth. OK, so crucially, we are allowed to choose 2 things. We're allowed to choose the time point t at which we make our prediction. So we choose when we are done seeing the past and are ready to make our prediction. We also get to pick the window length that our prediction applies to. So we pick the number of bits whose mean we're trying to estimate. Okay, and say we measure our loss in terms of just the mean squared error. Okay, so again, right? So you know, we pick this value t. We see data up to time t. We pick w, and we're trying to predict the average of these next w bits. And the maybe surprising thing is that there does exist a strategy such that Bob can attain an expected squared error on the order of 1 over log n, which is tight. Oh, so n is the total length of Alice's sequence. So we were playing this game. We can pick when to do our thing, but we need to make a prediction before time n. So n is kind of the window length in which we want to make some prediction. If we don't make a prediction by time n, then we get infinite loss. Say.
So if I have an infinite sequence, I can make an exact prediction?
Yes.
Is that obvious?
Is this obvious, the theorem?
No, I'm asking if it's obvious when n goes to infinity.
No. So okay, good. So okay, so this upper bound was shown in this paper of Andy Drucker. The matching lower bound is in this paper with Mingda from Colt last year. And yeah, so we were quite surprised that you can do better than constant error. So just to illustrate two little things. So if we don't get to pick, well, okay, sorry. So I'll tell you what the algorithm is, and then maybe it'll become obvious. So actually, you know, even though we're allowed to make this, to pick the time and this length of the prediction, we don't need to look at the distribution. We don't need to look at the data to do this. So actually, the same theorem applies even if the universe picks the time uniformly between 1 and n. And the window length, the number of bits that we try to predict, is picked uniformly from the set 1, 2, 4, 8, 16, 32, up to, say, n over 2. So we don't need to look at the data to do this. And what's the algorithm? Well, we'll just predict that the mean of the next w bits is equal to the mean of the most recent w observations. Okay, so like you know, we're outputting the mean of this as our estimate for this mean. Okay, and this. So the lower bound holds in the stronger case where we can, you know, where we get to pick t and w as a function of what we've seen, but that doesn't actually help. So is this obvious? So just two simple points. One is if this time t is not picked randomly, or if the adversary, if Alice knows the time t, then obviously you can't hope to do better than constant error, because the sequence could just be all zeros up to time t, and then do something funny afterwards. If the window length that we're trying to predict is any fixed window length, if there's no randomness there, then you can't hope to do better than a constant error. Also, if you can pick t, but you're forced to predict the average of the remainder of the sequence, you also can't do better than a constant. So both 1 and 2 are sort of, they need to have some randomness, otherwise you can't do better.
Sorry, when is the sequence fixed? Is it like, so what is the
Good,
ordering of
good, good. So the sequence is adversarial, but it's not adaptive. So think of it as before Bob enters the picture, Alice picks the sequence, writes it down on paper, and then is just, that's it.
Right, and then the algorithm chooses when it's going to make the prediction? So that's what how it's going to happen?
Yes, but it picks when, just uniformly, say, between 1 and n minus 1. Right? So it's not doing anything clever, right? OK, good. So let me just sketch a kind of intuition for what's going on, and then maybe there'll be some slides, but maybe we'll skip them. So suppose everybody knows that you're going to pick w to be 1. You're going to predict just the next value. Then what's Alice going to do? She can do lots of things, but one thing she could do is just to pick the sequence where each bit is a random coin flip, either 0 or 1. Given the past, you're trying to predict the next one value. You're not going to get error better than a half, right? An expectation. OK. However, if this sequence is really this adversarial sequence for w equals 1, if now I'm going to make a prediction over length n over 2, how accurate will our prediction be? Super accurate, right? Like squared error will be like 1 over n, right? OK. Now imagine Alice knows that actually we're going to pick w to be, say, n over 4. We're going to try to predict this really big window. Now what's Alice going to do? Well, she'll pick a sequence. Well, yeah, someone tell me. If you know I'm going to try to predict some big, long window, where the big, long window, say, occurs at a random time, what's the worst sequence that you could feed me?
0, 1, 1, 0, 2 ones, 4 zeros.
OK, sure. OK, so something where say blocks of n over 8 are constant zeros or constant ones, but it's a coin flip whether it's all zeros or all ones. So you have big long sequence of all zeros, then big long sequence of ones, maybe another big long sequence of ones, and more zeros. And now if I'm trying to predict a big block, there's going to be one of these big constant unknown blocks inside it, and I can't hope to do better than constant error on that. OK, so that's the worst case if I'm going to predict a huge window length of, say, n over 4. However, if that's the sequence I get, and I decided to predict w equals 1, I decided to predict the very next value, I would be doing very well, because big blocks are all basically the same, right? OK, so basically the intuition is that there's no way that you can make a sequence that's adversarial at all different time frames simultaneously. The sequence that's really bad if w is 1 is great if w is big. The sequence that's really bad if w is big is great if w is 1. Intuitively, what different time scales are there? Well, the time scales of predicting 1, 2, 4, 8. They're kind of logarithmic in n different time scales. If you balance how well you're going to do on all the different time scales, you end up with this kind of 1 over log n. And that's both the intuition for the algorithm as well as the intuition for the lower bound. OK. Is that kind of OK? So a different way of saying this theorem is, if you have a length n sequence, well, this is kind of informal. Like the moving averages at different time scales will mostly be quite accurate most of the time. There's no way of making a bounded sequence where your moving averages are all sort of completely off almost all of the time. There's just not enough variance. You just can't make, there's nowhere your sequence can go. So, yeah, sorry.
If there are only 0 or 1 random sequences, then it doesn't matter how large is the window you're going to pick.
Oh, so no. So again, we're predicting the average over a length w window.
But w when you say large w, what do you mean?
So if I know the sequence is random, I would try to predict, say, length n over 2 sequence, the average of it, and the average will be concentrated about a half with error, super accurately, right? Yeah. OK. OK, good. How many people find this theorem so surprising, at least? Yeah. OK. OK. Maybe let me sketch the lower bound proof idea just because it's kind of nice, and I think it can be used to do some other things too. OK, so again, the theorem is the lower bound. There exists some distribution over length n binary sequences. So the distribution from which Alice can draw her sequence such that no algorithm can choose the time t and window length w and estimate this average better than expected squared error, order 1 over log n. OK. Again, we're going to try to design a sequence that's kind of anti-concentrated simultaneously at all time scales as well as we can. Okay, so the idea is basically we're going to make this binary tree. The leaves of the tree will be the length n sequence. So there'll be n leaves of the tree. And the root of the tree starts with value 1/2. The values here and here will be 1/2 plus or minus 1 over, so there'll be some parameter k, which is going to, I guess, be the depth of our tree or something. And the values here will be 1/2 plus or minus 1 over, 1 over something small. The values here will be 1/2 plus or minus something a little bigger, until down here the values are 1/2 plus or minus 1/2. And we start with 1/2 here, and basically we're just going to pick the value here to either be 1/2 plus the thing or 1/2 minus the thing, and we pick it such that the expectation of this node is the same as this node. Okay, so this thing is picked so that the expectation is 1/2, so it's just probably 1/2, it's 1/2 plus blah, with probably 1/2, it's 1/2 minus blah. But once this thing, this thing is far from 1/2, or sorry, this thing is a bit different from 1/2, so then this thing will be picked to be an unbiased estimate of this, and so on. And I guess the key intuition here is, if this is the window we're trying to make our prediction on, there's always a fairly large subtree contained within this window. And the claim is just the variance in what we pick the root node of this tree to be is already going to create enough variance to get our 1 over log n lower bound on how well you can do. Okay. Is this sort of clear to them, at least super high level? Okay. So this is actually an illustration of what happens when you construct something with this. So it's the same sequence maybe, or different sequences. I guess different sequences. These are very different. So this is a moving average at the 2 to the 15 time scale. This is a moving average at the 2 to the 10 time scale. And you can see that they both look pretty anti-concentrated at these two very different time scales. I also wanted to just show a picture because this is quite different from Brownian motion. So when you start thinking about these lower bounds, the natural thing is, well, what happens if you just have some Brownian motion? And basically the problem is you can't get a good lower bound out of Brownian motion because sort of you do a Brownian motion, you try to squeeze it into this like interval 0, 1, and once you squeeze it, then you kind of squeeze out most of the variance, and it doesn't give you anything. And there are some other settings where, well, anyway, I think this construction might be useful elsewhere. Okay. Okay, so the proof of the upper bound, it's actually two lines. It's just an inductive proof where you argue what happens if n is 2 to the k versus 2 to the k plus 1. You just do a little induction on k, and it's literally 2 lines, and it works out. Maybe I won't show you. But what's going on in that 2-line induction proof is basically you're leveraging the relationship between potential test and training sets. So wait, where is my, oh, good. So yes, in every realization of this sort of setting, you can think of it as the training data is chronologically before the test set. However, when you think about, well, you're picking t at random, you're picking w at random, sure, today, or in this instance of the problem, we have this training set and that test set. But we could have also had this training set and that test set. And the potential training sets, or the potential test sets, do overlap with the potential training sets. And basically, that's what we're leveraging. Okay? Whereas if t were fixed, then there's like never any overlap between the potential set of training sets and the potential set of test sets. Okay? So what's really going on here is we somehow have this potential train sets, potential test sets are overlapping in this sort of interesting way determined by the distribution from which we're picking t and w. And the much broader question is, well, when can we leverage other sorts of relationships between potential train sets and test sets to get sort of unexpected results or unexpected algorithms? OK, so I'm going to change gears and start talking about this kind of more general setting of which this is going to be a special case. So any thoughts or questions on this sort of sequential setting before I move on? OK, good. So what are simple sorts of relationships between a test set and a train set that we sort of intuitively understand how to leverage? OK, so one silly example is just importance sampling. What's that? Oops. OK, maybe ignore these pictures. So we all know kind of what importance sampling is. This is just data points are still independent. Like each data point, say, picks independently, is it in the training set or the test set? But some data points I know, well, the probability that they're in the training set is, much higher than the probability they contribute to the test set. Okay, that's one way of thinking about importance sampling, and we know how to correct for this, and everything is fine. A different thing where there's an interesting relationship between the sort of test data and the training data, which we don't really understand, is what's referred to as snowball sampling or chain referral sampling. How many people have heard of this? OK, it's curious that, like, I don't know, even statisticians don't know of this, and yet sort of anyway. So what is this? This is it's kind of a viral process on a social network. And so this is kind of a medical sociology technique. It's been used a lot to estimate attributes of kind of sensitive populations, drug users. It was used a lot to collect data in the early days of HIV and AIDS. So basically what happens, you have someone come in who belongs to this sensitive demographic. And then you sort of ask them to fill out a survey. And then when they leave, you say, hey, all of your other friends who are also in this sensitive demographic, please have them fill out one of these surveys. For each of your friends who fill it out, I'll give you $10, and I'll give them $10. Okay? So then you have this kind of viral process. This person comes in, and then maybe some of their friends come in because of them. And then when they come in, you give them a stack of surveys, and you get their friends, and so on. And say we do gather data in this way via this viral process for t days, and now we want to predict something about either the set of all these users, or of all of these individuals, or maybe our test set is just the people who come in on the t plus first day or something. Okay. So in what cases can we actually do learning or estimation in this sort of interesting sampling procedure? Or what sorts of social networks have the property that there is some algorithm that you can use to, say, even predict the test average given the training average, where the test set is drawn from the people who come in on t plus first day. The training set is the people who contribute their data in the first t days. Okay. OK, so let me describe a general formulation that kind of encapsulates have all of these settings. OK, so we're going to assume that the data itself, each data point is just a single number and is bounded between 0 and 1. However, we assume that we know a distribution from which the test train partition is drawn. Okay, so suppose, OK, so we'll flesh this out again, but so we know the distribution from which the test train partition is drawn, and then at game time, the universe picks a train test partition according to this distribution. We see who's in the train set, who's in the test set, and we're asked to predict, and we see the labels, we see the data values in our training set, and we're asked to predict, say, the test mean. Okay. And again, we're going to be evaluated based on the squared error how accurate is our actual estimate. Okay, so think of the following. So suppose this is the domain of our data points. So we have a bunch of people. Say we're trying to guess the mean salary for some test set of people, and the salaries are all picked adversarially. And there's some distribution over who's in the training set, namely, which of the employees fill out the anonymous, or sorry, which employees fill out the salary disclosure, right? And then, so there's some partition that's actually picked from this distribution. This is our training set. This is our test set. This person is in neither the training nor the test set. Namely, we don't see, people in the training set, we see their value. And we're asked to predict what's the average salary of these people. This person, G, they're not in the training set. We don't see their value. But they're not in the test set. We're not asked to predict, to predict anything about them. OK. And if you give me an algorithm that takes as input a distribution, it takes as input the distribution over this test train partition, and it takes the given training set and test set, and the training values, and it outputs an estimate of the mean on the test set, we evaluate this algorithm as the max over data labels. So for worst case data, we're asking what's the expected error, where the expectation is over the randomness of the algorithm and also the randomness of which split we actually ended up with. So is this problem formulation sort of clear? Yeah.
Sorry, this might be a little bit trivial, but what if your distribution assigns certain people only to the training set and then the rest to the test set? And
perfect. So, OK, good. So suppose this distribution over test chain splits is as following. Suppose each person has some secret number in their head, and the distribution is, this half of the room is either always in the test set or always in the training. Sorry, this half of the room, say, is always in the training set. This half is always in the test set. Then how well can you predict? You can't at all, right? Like you'll get constant error because there's no sort of connection. Okay, right, good. The opposite side of that spectrum, so let's just do a couple of examples. Suppose we do the random partition. Sorry, all the answers are given, sorry. OK. OK, so suppose our distribution over test train partitions is as follows. Each person will either be in the test set or training set, and they flip a coin with probability half they're in the training set, probability half they're in the test set. Even if everyone's value is a worst case value, say bounded between 0 and 1, with respect to the randomness of this partition, all we need to do is output the average of our training set, which with high probability will be within 1 over root n of the true average, which with high probability will be within 1 over root n of the test set average. Okay. So this is should not, right? This is fine. Right, so worst case data is fine if you're completely independently randomly picking the test and training set. OK, say each person is in the test and training set independently. Say they're in the test set with probability p and the training set with probability 1 minus p. Okay. So sure, there's some people maybe who are never in the test set and are always in the training set. What do you want to do with their data? You want to ignore them, right? If they're in the training set, you know they'll never be in the test set. So, and similarly to the independent case, you can cook up an unbiased estimate of the expected value of the test set. And if things concentrate, then, okay. And that's important sampling, basically. These two cases are sort of easy. Why are they easy? They're easy because the expected value of the test mean is always going to be the same as the expected value of the training mean. In this example that we saw at the beginning, where the training set is, you pick a random t between 0 and n. Training set is x1 through xt. Pick a w according to some distribution. Test set is xt plus 1 through xt plus w. So in this case, it could be that the test mean, like the expected value of the test set is not necessarily the same as the expected value of the training set. If my data values start at 0 and they go 1 over n, 2 over n, they linearly increase from 0 to 1, my test means are always going to be fairly different from the training means. Yet despite this, what we showed is you can still do accurate prediction despite the fact that the test means are anti-concentrated and in particular are not concentrated about the training mean. OK, and then there's also this example, which maybe I haven't described formally enough to even know that there is an answer. But there are certainly more difficult distributions that are still kind of very well motivated that we might want to consider. OK, is the problem formulation clear? If not, you should ask questions. There's probably other people have questions too.
So the distribution of the train test split cannot depend on the data label?
No. So think of it as, again, there's us, the predictor, and there's the adversary. The distribution is fixed. Everybody knows I know the distribution. The adversary knows the distribution. And then the adversary will come up with labels to make my job hard. And I want to come up with an algorithm that, even with worst case labels, sort of leverages the connection that's present in this distribution to do well. So one very slight subtlety. So in this case, I'm assuming that you know who's in the test set. Like you know who's in the training set and who's in the test set. And then you also know the labels of the training set values. Right? So here I know that G is not in the test set. You could also think of a version of this problem where I don't actually know who's in the test set at all. Okay? And that's sort of from a it's harder to make good algorithms for that setting, but it's a simpler setting, so it's easier to analyze. But I think this is maybe a good setting to start with. OK. OK, so let me tell you a few things about this setting. OK, so one kind of very naive conjecture. Maybe it shouldn't be called a conjecture, because it's not true. But one naive thing would be to say, well, maybe for every test train split, there's a good predictor which is return some weighted average of the training data. And the weights will depend on what the specific test train split is, as well as what this underlying distribution over test train splits. But maybe there's always a linear predictor that returns a convex combination of these training weights. Like in the selective prediction, in the sequential setting, that's what we did. We returned a weighted combination of the training data corresponding to weights 1 on the previous W things and 0 before. OK, so it actually turns out that even among these linear schemes where you're returning a weighted combination, the weights can be negative. And there's sort of simple instance of this. Suppose we just have 3 data points, x1, x2, and x3. And the distribution over test train splits is as follows. With probability a third, we just see x1, and we ask to predict the average of x2 and x3. With probability a third, we just see x2, and are asked to predict the average of x1 and x3. And with probably a third, we see x1 and x3 and asked to predict x2. If you ask what's this kind of minimax optimal linear algorithm, it turns out to be the following. So in this case, we see x1, and we're going to predict that the average of these two is 0.4 times x1. In this case, we predict that the average of these two is 0.024 times x2. And in this case, we predict that x2 is minus 0.2 times x1 plus something times x3. Okay? And so these negative weights aren't they're a bit upsetting, but they aren't so surprising, right? So in some of these kernel things, you end up with negative weights too. But basically, this comes about as sort of it comes out because of this minimax version. So if you were the adversary, you're going to say, oh, here I'm using x1 to predict x2 and x3. Here I'm using x2 to predict x1 and x3. And any reasonable algorithm will do really, really well if x1 and x2 are correlated. So the adversary is going to say, I want x1 and x2 to be really anti-correlated. And by putting a negative weight here, you're sort of saying, well, if you make them really anti-correlated, I'll still do well. Anyway.
So when you say weighted average, what you mean is positive weights, but they don't have to sum to 1? This is your definition of what weighted average is? So the first two are not a problem for you here?
That they don't sum to 1? Yeah.
Okay.
Yeah.
So,
So in the case,
a more reasonable conjecture would be the best linear predictor does as well as any predictor.
OK, good. So that's actually not true either.
Okay.
So right. So the optimal predictor actually can be nonlinear, which is pretty upsetting. And so we did some big brute force search. There are these. An example, even with 4 data points, this is the distribution over partitions. The optimal linear thing is a kind of 0.666, and then there's a nonlinear thing that does 663. Okay. So the revised conjecture that maybe there's a constant factor gap between the best linear and the best nonlinear, but we don't know.
Okay, but I mean, if you prove anything like this, you're not going to be able to capture this kind of constant. I mean, do you really want to get the actual value of this minimax thing? You want to get some bounds as the number of points goes to infinity or something like this?
So what I want is I want an algorithm which you give me this distribution. It tells you an algorithm which is, say, within a constant factor of the best you could hope for this distribution.
Okay.
That's one thing.
But it could be that the linear predictor does this.
It could be, and I think it is. Okay. We'll. Okay. So again, this is right. So we're trying to minimize over algorithms, maximize over the adversarial labels to the points, and say we're trying to minimize the this maximum squared prediction error. So for the time being, ignoring this issue of linear versus nonlinear, so one sort of natural starting place would be to say, well, say we restrict ourselves to linear algorithms. What can we even say? So, and actually, never mind. Let's ignore trying to find a good algorithm. Say someone gives us an algorithm. Can we even evaluate the worst case performance of that algorithm? Okay. So how hard is this problem actually? Good. So let me describe a distribution and describe an algorithm, and then you guys can tell me how hard it is. And I hope it doesn't reveal the end. OK, good. OK, so suppose I give you a graph with n nodes, x1 through xn. Each node is going to have one number sitting on it. And the distribution over test train partitions is as follows. We're going to uniformly at random pick an edge, ij. Your training set will be xi, and your test set will be xj. Okay? So your training set is just 1 point. Your test set is just 1 point. And suppose the algorithm is I'm going to predict that xj equals xi. Right? You just predict that the test average is this training average for these single points. OK. So this is what you're going to do. How hard is the problem that the adversary is solving? So what is the adversary going to do? Or how accurately can we hope to do this if the adversary is labeling the x's according to the worst possible 0, 1 labels? Oh, this is great. Yes, it's exactly max cut. Okay, so this is literally, this is literally what max cut is. We have a graph, and we're assigning 0s and 1s to the x's, such that what does the adversary want? The adversary wants xj to not equal xi. That's literally the definition of max cut, right? OK, good. So So immediately we start to get a bit pessimistic, right? Because it's NP hard. And remember, this is just what the adversary is doing. We're trying to like get a good algorithm, right? But even evaluating how good a really simple algorithm is in a really simple case is NP hard. But of course, you can approximate this to pi over 2. This is this Grothendieck problem. So OK. I have, what, 4 minutes, 5 minutes? Something like that. OK, so it actually turns out that for any distribution over test-trained partitions, and for any linear algorithm, you can estimate the performance of it. Basically leveraging this kind of Grothendieck problem. This you can formulate it as a STP and get this pi over 2 relaxation. And then kind of the nice part is that why does my screen not look like your screen? Anyway. OK, so basically, you can do some convex duality to flip these things. You can do some closed form for this minimum over algorithms part. And at the end of the day, you can actually get a 2 over pi over, whichever one of these is not like better than better than 1. 2 over pi approximation to the best linear estimator. So again, this is saying that we're going to return a weighted combination of the training labels, where the weights can depend arbitrarily on the distribution and on the test and training sets, but we don't look at the training values to determine the weights. Okay, so that's the class of algorithms that we can say. And we get this pretty good constant factor approximation, a multiplicative approximation to the best for these linear schemes. And actually, this distribution over partitions, right, this could be some exponential sized object, but it's OK to just sample from it. And you can just sample some polynomial n times and still get this algorithm to work with just a little extra additive dependence on the number of times you're willing to sample from this distribution. OK. Good. So let me just finish with some future directions. So in some sense, this gives a characterization. This result gives a characterization of the best performance you could hope to do with this kind of linear algorithm. Although it's phrased in terms of this kind of STP on these kind of strange sets. It'd be really nice to get very simple characterization. What property of a distribution over test-trained partitions do you need to, say, get subconstant error? That would be really nice. Then there's a question of, well, linear algorithms are not optimal, but I strongly believe that they're within a constant factor of being optimal. But proving that seems challenging, but maybe doable. OK. Then there are things like, for important sampling, all you need is the marginal probability that each point is in the test set versus training set. Can you come up with a simpler algorithm that sort of does something reasonable if that only depends on, say, the correlations between, how correlated is it that x1 is in the test set versus x2 being in the test set? Can you have something that leverages just these pairwise correlations that is sort of, think of it as the correlation analog of important sampling? For certain special cases, things like snowball sampling, I think it is actually worth sort of understanding when and how you can debias things. So for what social networks are these viral sampling type things, can they be debiased? And then another kind of nice, so throughout, we've just been thinking of data points as being single numbers. We're trying to estimate the mean. Given the ability to do this in a black box fashion, you can also do things like regression, right? Like if you compute the optimal regression vector on some test set, this, if we're in d dimensions, this involves estimating some d by d matrix and so on. But you can pointwise estimate each of these elements just using mean estimation. So there are kind of reductions between, if we can estimate the mean, we can do things like regression. But I think maybe we can do better than, we don't need these d squared blowups and so on. And it is worth thinking about these higher dimensional, more learning type things like regression. Okay, let me just end with this. So, good. So if this is kind of the usual, learning from independent samples, I've sort of described this problem of worst case data, but knowing the distribution over these test train splits, this is one kind of far departure from this setting. There's also this robust learning, the contamination models. There's, of course, online learning in this kind of regret minimization formulation. And I think it is worth thinking of, what are other sorts of plausible departures from this sort of independent setting. Thank you.